Hello everyone, welcome back. If you are new, this is a new series that we have started wherein I am trying to dissect segment trees from scratch. I already uploaded two different detailed video in the past in this series. The first video we talked about the basics of segment trees, how to build it, when to use it, how to do point update, range queries, how to derive the time complexities of each of them, how to like what is the pseudocode and how to we also look at a sample implementation using a very simple problem. In the next video, I talked about a second class of problem, that is you are asked to find queries on a prefix of an array. And we saw how that can be solved using point update and range queries itself. Notice that we haven't introduced lazy propagation yet. We are just trying to strengthen our understanding of point updates and range queries and see how powerful these two themselves are without even lazy propagation. So in this class of problem, I introduced one sample problem previously, that is counting the number of smaller elements in the left, right? And as discussed in the previous video, the next few videos in this series would just be solving problems on this technique itself. So in this particular video, we will be solving this particular problem, enemy is weak. In the next video, I would be tackling this problem, and in this video, I will also give you a small hint how these two problem differs so that you can try the second problem yourself as well. So with that, let's start with the quick recap of the last thing that we have discussed in the previous video. So we have solved the problem of finding number of smaller elements in the left. So let's say you are given an array. You need to just simply find out the number of smaller elements in the left of every index I. So let's say this is index I. You need to figure out how many elements are smaller than 6 in the left. So you can see there are two elements, 3 and 1, which lies in the left of 6 and they are smaller than 6. So for this particular index I, the answer is 2. Similarly, for this particular index, the value is 9. So you can see there are 6 elements, 2, 4, 6, 1, 3, 8. All these 6 elements lies in the left of 9 and they are smaller than 9. So hence, for this particular index, the answer is 6. So you have to just return this array where each element denotes the number of smaller elements less than that particular index, right? So we looked at how AVL tree or any balanced binary search tree can help here very briefly, but we primarily focus on solving this using segment trees, and how we have end up doing it is we sorted the array, and we after sorting the array for any index I, we know which index this will map to in the sorted array, right? Now, once we have figured out this index, we already know that everything in the left of that particular index would be smaller than this 6, right? So what we now need is finding out how many of these elements actually lies in the left, right? Because this is the sorted array of the entire array. So you can see only 3 and 1 lies in the left, but 2 and 4 are also there in the left because they are smaller than 6, but 2 and 4 lies in the right. We only need to count the number of elements which lies in the left. So that's where what we said, that we will simply maintain each a binary array where every index would be either 0 or 1. Now every element in the left we will just mark as 1. So 10 we marked as 1, right? 8 we marked as 1, 3 we activate, so we marked as 1 for 3 and 1 as well, right? Now to find out how many elements are smaller than 6 and lies in the left, we can simply do a range sum in this particular L2R, right? And range sum would give us the number of elements which are smaller and lies in the left. Why? Because querying in the left would already mean that we are querying everything that is smaller than 6. What we just need to know that how many lies in the left, and we have only set those indexes which are actually in the left. So if we do a range sum, we will get exactly how many elements are in the left and smaller than 6, which we want, right? So that's how we will perform queries. So as and when we do 6, before processing the next query, we will activate 6 as well. So that's where we will keep on doing this while traversing from left to right, and finally we will have this resultant array for each of the indexes, right? So if you have any doubts in this particular recap, I would strongly encourage you to watch the previous video first, because this video would just be an application of the previous video. So strongly encourage to watch that. Now, as discussed in this particular problem, we will be focusing on, in this particular video, we will be focusing on this particular problem of code forces, enemy is weak. So this is a fairly hard problem. If you are aware of code forces, level E actually is a hard problem. So we will see how easy this problem is with just the trick that we have discussed. So the problem states that you need to find the weakness of an army, and weakness of the army is defined as the number of triplets I, j, k such that I less than j less than k and ai greater than aj greater than ak, where ax is just the power of man standing at position x. So basically, you are given an array. You just need to find out the number of triplets I, j, k such that I less than j less than k and ai greater than aj greater than ak. One thing to note here is all the n elements are distinct, right? All the elements in the array A are distinct, right? So we'll look at how this will help, but for now, this is the criteria that we need to satisfy, and we need to figure out how many triplets satisfy this criteria. So in this particular example, there are two pairs or two triplets that satisfy these criteria. First is 0, 1, and 3. So I is 0, j is 1, k is 3. So you can see I is less than j and j is less than k, right? And similarly, ai, which is 10, is greater than aj, which is 8, and which in turn is greater than ak, which is 3, right? So this satisfy all the constraint. Hence 0 1 3 is a valid triplet. Similarly, 0 1 2 is also a valid triplet. So I less than j less than k, and you can see ai greater than aj greater than ak. So there are only two possible triplets here which are satisfying this constraint. Hence the answer here is 2, right? Now how to solve this? So firstly, the very brute force solution could be you just iterate over all the three indexes and figure out how many of them satisfy this criteria. So you just iterate over I, j, and k, and this would be plus 1. So you will see, you will just simply make sure that I is always less than j, which is always less than k. So you always make sure that criteria with this form of iteration, and after this you will just check whether ai is greater than aj greater than ak is satisfying or not. If it is satisfying, you will increment your result, and finally your result variable would contain the number of triplets that satisfy this constraint, right? Now the complexity of this algorithm is order n cube, right? But n cube would not pass here, even n square would not pass here, because n is up to 10 to the power 6, right? So we need to do something better. Now we need to remove, let's first try to solve this in order n square before jumping into order n log n or something of that sort. So we have to reduce this from n cube to order n square. Now what does that mean? It means we have to remove one of these loops for sure. Let's try to get rid of the last loop. Now what does this mean? This means that we are not allowed to iterate over all the k. So, and still we want to find out the valid case. Now what are the valid case? The valid case are the ones which lies in the right of j, right? And their values their values are actually less than the value of j, right? So those, you have to find out the number of such indexes k which exist, and you can simply, like, instead of doing result plus plus, you will do result plus equals that value, right? So basically the pseudocode would then translate to something like this. So you will iterate over I and j, and inside the loop you will, instead of iterating over k, you will simply figure out how many elements or how many indexes k are there which satisfy this constraint, or in other words, you have to find out how many indexes are there which are in the right of j and which are smaller. So basically this problem, count smaller right, is exactly similar to this problem, which is it's just that we have to count the number of smaller elements in the right. So instead of iterating from left to right, we will iterate from right to left. and by doing so, we will be activating only the right indexes, and we will be able to make sure that how whichever index is one are the ones which lies in the right, and the same technique would work there, right? Now, what is the complexity of this particular solution? The complexity would be order n log n for finding out this array count smaller, right? Because you need to first like sort the array and also apply range queries and point updates several times. So this would take order n log n to build this array, right? After that, you can simply do two for loop, and inside this operation would just be order one because you have already calculated it outside of this entire structure. So the total complexity would be order n log n plus order n square. Now, if you are new to this problem, sorry. So if you are new to this problem, I would encourage you to even code this particular solution as well, because this would give you much better insight and much better understanding of what we have discussed previously, right? But as you know, this solution also is not the final solution, because n square is something which will also not pass. So we have to reduce this n square as well. So what does it mean that we have to reduce n square? It means that we have to remove one of these loop as well. Now, which one of these two we will remove? You can try removing this particular loop, but you will, sorry, you can, yeah, you can try removing j, but you will see that you will not be able to figure out j and k without actually fixing one of them, right? So that's where, in this kind of problem where you are given these three indexes, we'll always try to fix the middle one, or the one which basically will segregate the array for the left remaining two indexes. So let's say if you fix j, you already know that I will be in this part and k will be in this part, right? But let's say you have fixed I. So if you have fixed I, you also, you just know that j and k would be in this part, but you don't know how, like, in which range j would belong to or in which range k would belong to. That's where once you fix j, you are able to deterministically say that okay, I will belong to everything, like I would belong to one of the indexes which are in the left of j, and k would belong to one of the indexes which are right of j, right? So that's why we will try to fix j instead of I. So we will try to remove this particular loop from here. Now, what does this mean? This mean that we are now saying that we have fixed ij. Now tell me how many i's are good for this j and how many k's are good for this j, right? And then let's say there are total a number of i's which are good, and the total b number of k's which are good. So in total there would be a into b triplets which will be good for this particular j, right? And you will do the same for all the j, and finally you will get the answer, right? So the pseudocode would now translate to, so this was the current pseudocode, right? So this pseudocode would now translate to something of this. So basically what you will see, you will fix j, and for each j you will try to find out the number of larger element in the left of j, right? And number of smaller element in the right of j, right? And with these two you will be able to uh, like whatever the value is, you will just multiply them, because let's say there are two i's which are valid for this j and there are 1k. So you can use one I and pair up with this j, with this, with particular k, and similarly you can use second I and pair up with the same k. So each of these I can be paired up with all the k's, hence you will simply multiply them, right, to get the answer. So hope this particular point is clear. Now what we need is, we just need to find out count larger left and count smaller right, and we will be done, right? So let's just try to take one small example and understand this. So this is the algorithm that we will be applying. So let's say you have figured out count smaller, count larger left and count smaller right. So basically for each j, you know how many ais are valid, right? And similarly for each j, you know how many ak's are valid or how many k's are valid. So here the value here is 0 because for this particular, if j is this, there is no valid I, right? Similarly if j is this, there is one valid I because which this I lies in the left, and also AI is greater than AJ, right? So 10 is greater than 8. So that's why this there is one valid pair, and hence the value here is 1, right? Similarly, let's say if this is the J, then there are both this I are valid. Why? Because first of all they satisfy I less than J, right? And second thing, they also satisfy AI greater than AJ, like they both lies in the left and they both are greater, so hence the value here is 2, right? So let's say we build this array and we build this array. Now what we can simply do, we can simply iterate over j and just multiply these three. So 0 cross 3 plus 1 cross 2 plus 2 cross 0 plus 2 cross 0, so finally it would come out as 2, and this 2 would be your answer, right? So now you just need to build these two arrays. We already saw how to build this array using using the same segment tree trick which we have used to find out the number of smaller elements in the left. We can use exact same technique and build one more segment tree and figure out how many elements are larger and present in the left, right? So how we will do that? Again, same trick. Instead of uh, querying in the range in the left of 6, you will be querying in the right of 6, right? That's the only thing that you will do. And you know that because you have activated only the indexes which are in the left, so the sum in this particular range would give you the count of indexes which are actually greater than 6 and lies in the left of 6, right? And that's what you want. Like you want all the elements which are greater than current index and also lies in the left. So what we can simply do, we can simply maintain two segment tree, one which will help us find this, and second which will help us find this. And find once we get these two array, we can simply multiply each of this position and get the answer, right? Now if you think a bit further, you don't need to maintain two segment trees as well. You can simply maintain one segment tree and solve like one segment tree, and let's say you figure out this particular array. So from this array itself, you can derive this array without a segment tree. How you can do that? That I will explain after some time. But for now, if you are new to this concept, I would strongly encourage you to pause the video right away and try to get this particular problem submitted by coding this and this separately, right? Now I will show you the code for finding out counting the elements which are like which are in the right and which are list. So this is the segment tree code, which is the standard segment tree that we have just we have looked at in the past in this series. So here we have to do range sum, and because we have to do range sum, the value that would be that we would be returning from query would be 0, because we know 0 will not affect the final output because 0 plus x will be 0. So if the sum was x, adding 0 there would not affect at the final output x. That's why if the range is completely over like completely outside of range x and y, we will simply return 0. Otherwise we will return the if it is completely overlapping, we'll return the current value in the tree. Otherwise, we will go both left and right and just call the same query, right? Now, this x and y is the range. For those who are new, this x and y is the range which we are trying to query. And this LRI is something that we are using to represent a particular node of the tree, right? Now, what we are doing, we are simply figuring out uh, how many elements are there which are in the left and uh, which are in the right and are smaller, right? So For that, what we have done, we have first sorted the element, because if you remember, that's what the first step was. We sort the entire array, and then we figured out the mapping. So 10 belongs to index 7 in the sorted array. Similarly, 8 belongs to index 5 in the sorted array, and so on and so forth, right? So we sort the array, and we made, like, we figured out the indexes of all the position in the sorted array, right? Now notice that we are able to do so because each element occurs exactly once. Each of these elements were different, right? That's why we are able to map this one to one. Otherwise, we will not be able to map this one to one, and that would be something that I would give you as a follow-up, and we'll discuss in the next video. So first, for now, because every element is unique, we can simply map them one to one and figure out the positions of each element in their sorted array. So for 10 it would be 7, for 8 it would be 5, and so on and so forth, right? Finally, what we have done, we have simply figured out the number of greater element. To figure out the number of greater element in the left, what we have done, we have query. First of all, we are iterating from left to right, right? And we have to find out number of greater element in the left. So while iterating from left to right, notice that at the end we are updating the current position as well, where position is the position of the current element in the sorted array. So for 10 it would be 7, and for 3 it would be 2, right? So because if we are at index I, and we are sure that all the position up to I are actually marked, right? Now to figure out how many elements which are greater, we can simply do a range query in this particular range, and that would range some query in this particular range, and that would give us number of smaller elements, a number of greater elements which lies in the left, right? So that's what we have done. We have simply queried in the range position plus 1 to n minus 1, right? Now once we have figured out the greater element in the left, what else we need? We need two things, right? Number of elements greater in the left, and number of elements which are smaller in the right. So either you can maintain tree 2, like second segment tree, and do that query, or as I have mentioned, you can simply derive uh, this array from this array, or vice versa. So what we have done, so let's say you sort this array. So array was 10 at 1 3. Now you sort the array, you make it 1 1 3 8 10. So once you sort this array, how many elements are there which are smaller than aj? So let's say this is the current j. So how many elements are there which are smaller than aj? One element, right? Like two elements, right? 1 and 3. Now how many elements are there which are greater than aj and lies in the left? So you already figured out this point by using this segment tree, right? So you already know that this is, let's say this value is 1, right? Now once you have figured out this, you can simply figure out how many elements are there which are less than aj and are in the left of aj, right? So there are one element in the left, right? There's only one element in the left, and you already know that this there is one element which is greater than aj. So number of elements which are less than aj would be 0, right? And total number of elements which are less than aj is 2, and among these two, 0 elements lies in the left. So how many elements would lie in the right? Two elements, right? So just to reiterate this part, we what we want how many elements are there which lies in the right and are smaller than the current value 8, right? So for that, we simply figured out how many elements are there which are smaller than this 8 and lies in the left, and we can simply subtract it from how many elements are there, how many total elements are there which are smaller than it, and we will get the other part, right? So you can just play around this part a bit, you will be able to get it. In crux you can apply segment tree for this particular part as well, or you can just do some small mathematics to figure out this particular part. Once you have figured out that, you can simply multiply these two part and get the answer, right? So hope this entire problem is clear. Again, even if you watch this till this point, even if you have seen the code, I would strongly encourage you to code the segment tree part as well as the entire problem and get it submitted by yourself, because that would give you much more insight into the problem, right? Now coming to the follow up and the content of the next video. So as we discussed, we are able to apply uh, a map here, or a simple map of int comma int here, because each element here are distinct. But let's say this is not the case, like element here are not distinct. Now how will you map this? So this is a very simple problem. The same problem would be, or the same trick would be applied in the second problem that we'll be discussing in the next video. So I would encourage you to try this particular problem at least by yourself once before watching the next video in the series. So hope you enjoy the solution. If you like the video, give thumbs up and do subscribe if you haven't already. That will help you getting a notification as and when I update uh, a new video in this series. So with that, stay tuned and I will see you in the next one. Thank you.